This is what we discussed, right? The single phase thing. Okay. So we have this source current here. We have this source here, some AC source. So I assume this is single phase AC source. So I designed this is 230 into square root. So we need to give the peak value. So after that we have this diode bridge rectifier. We have this diode bridge rectifier. So here I'm measuring the source current, and here also I'm measuring the inductor current, and also I'm measuring the output voltage of this diode bridge rectifier. I assume this is Vs mod. So I think this is visible, right? So this is Vs mod. I connected a switch here. I connected a switch IGBT here. So here, remember, you have to make sure that the switch must have, so this switch doesn't contain a anti-parallel diode. Okay. So this is a simple switch. So anti-parallel diode is not required. We have this inductor, and after that I connected a diode. So this is the diode, and I connected a capacitor, and after that a load is connected in parallel with the capacitor. And actually I'm measuring the output voltage here, V0. So this is VDC. Clear? So this is circuit I developed here. So next thing is we need to measure the come to this controller. So in controller, what we have first, so VDC we need to measure, right? So you see the bottom. So VDC we have, so this is where I assume that the peak value is 230, right? So what if the peak value is 230, that is 230 into root 2. So in that case, it must be, I think it is 1.4, somewhere around 325 volts, or you will get 325 volts is the peak value, right? So the output voltage or the reference voltage must be greater than 325 volts. So therefore, so I selected 400 volts here. After that, we have this PI controller. So I had taken some gains as 2 and 5, or 5 and 2, you can take anything, because this PI controller will work best with this DC signals. So you can take any random value between 2 and 5. Right. So this one will generate the I maximum. The highlighted one is generated the high maximum. So this I maximum we need to multiply with the mod sine omega t, right? So this is Vs mod. So that is the output voltage of the bridge rectifier. I divided with this Vs mod. So with this peak value, so this is Vm here. Okay. Just a minute. Right. I divided with this Vm max, and after that I multiplied here. So this will be generated the current reference I maximum. So this is generated the current reference I maximum. One second. Okay. So this is generated the I maximum. So after that, so this is the reference inductor current. So we are actually comparing with the reference inductor current, this actual inductor current, this IL actual, right? So this plus minus, and after that I implemented a triangle carrier current controller. Right? So this triangle carrier current controller. So after that, right? So we have this comparison. So modulating signal is actually compared with this reference signal, and so on, right? So this is generate the firing signal for the switch S. I assumed consider a triangle carrier. The frequency of this triangle carrier is, I think, around 10,000 kilohertz, 10 kilohertz. Clear? The same thing I implemented, but without the notch filter. So let us see how it will work. Just a minute. Yeah, now it is running. So we have this VSIS, right? So we have this VSIS so that we can see that so both voltage, source voltage and source current are in phase. I just used some multiplier so that generally the voltage value will be higher, right? So you cannot see the proper relation of proper waveforms. Just I divided this with 1/5. Yeah, you can see the waveforms, right? The yellow one is the source voltage and the blue one is source current, right? The blue one is source current. You can see that the waveform is slightly bending, right? So why? Because this is due to the presence of third order harmonic, right? This is due to the presence of third order harmonic. You can actually see that. Similarly, we can see that DC output voltage. See here, this is the output voltage. It's supposed to maintain 400 volts. So we have 400 here. So here we have 400, right? So here this is moving, and this is I think somewhere. So this lowest part is somewhere around some 300 or some oscillations are there, right? Okay. So this is maintained between 395 and this is 400 for 402. Some 10 ampere ripple is there. Okay, and this ripple, most of the content is this third order harmonic only, so that you can see here. So if you know, you're aware that how to see the harmonic spectrum, right? If you see the harmonic spectrum for the source current, so we have the source current. This one is the source current. You can see the source current, right? So here if you notice that the THD is around 13.6%. So THD is around 13.6%, and you have this larger, this third order harmonic. You can see this third order harmonic. So this is roughly around 13%, greater than 13%. Again, you have the small values of this fifth order harmonic and this seventh order harmonic, again ninth order harmonic. These values are very small, relatively small, but the dominant one is this third order harmonic. So due to this third order harmonic, this waveform is not in a proper shape. So, but in fact, so it's maintained some unity power factor. but the power factor is means look like in phase. See, these are in phase, right? So this is, you can notice that this origin is 0 here. So here also this origin is 0. So both are meeting together, but the waveform is not a pure sine wave. So therefore what we have to do is we need to insert some notch filter. So this is the notch filter, right? So if you open this one, so here we need to take some quality factor. You might have aware that maybe you will study in other course, maybe in power quality course you might have studied this. So how to design a passive filter. So this is notch factor. You might have already studied this quality factor in designing series resonant and parallel resonant circuits. So this is quality factor. We can consider anywhere between less than 10. So this is a notch we are eliminating, right? So we are notch, it is eliminating, and the notch frequency I selected as 100 Hz. The notch frequency is selected as 100 Hz. You can actually see the response here. If you inherit this, you can see here. Yeah, you can see here the dBs for this. See here, this is corresponding to 0.2. So that is a normalized, that is 2%. So this is 100 Hz, yeah, it is given, right? So this is corresponding to 100 Hz. So we have this notch here, right? So this frequency, this is how much it is, that is minus 45 dB. So this frequency is reduced here. Okay, you can see here, right? I think this is visible. So corresponding to the 100 Hz, so this is notch frequency. The rest of the components, it is allowing. So only 100 Hz components are trapped inside this filter. Okay. The system is slow actually. It is continuously on for 4-5 days. Okay. Just a minute. I inserted a filter. Okay, I'm also seeing the response of VDC before and after filter. Okay, we are seeing the response before and after filter, so this helps in tuning that filter, right? So now we will see. Now we'll run again and we'll see whether it is actually working or not. Okay, so first we'll see the response of this filter. See here, the blue one, this is the yellow one is the actual output voltage, and the blue one is the filtered one, right? You can see that whatever that ripples are there, right? The ripple content, it is eliminated, right? You can see here. So here, this is the blue line. So this ripple content is eliminated. You can see actually this ripple content is eliminated, right? See here, this is the yellow one is the main one, main unfiltered output, and this is the filtered output. Okay. So now we can see the voltage and currents. See here. So earlier we have this third order harmonic. So now it is removed. You can see here, right? Okay. So earlier we have some third order harmonic component. So we can actually, that harmonic component is actually removed, right? If you closely observe that, so there is some disturbance here. You can see here, right? Some sort of disturbance still present. Okay, I think, right, you can see here, right? Some sort of disturbance is still present. So this is due to some harmonics, second order harmonic again. See, this is instead of that, this is flat here. Clear? So now this is the output voltage. So the output voltage ripple is very much reduced. As earlier we have the ripple is around, I will show you on a larger scale. This is 420. So this is varying from this, the bottom one is the 0, right? This is 0 here, from 0 to 420. You see here that ripple is almost 2 volts or 3 volts. So earlier the ripple is around 20 volts. So now it is reduced to 2 volts or 3 volts. It's a very small value. So you can also see the harmonic spectrum, so where the third order harmonic is eliminated. This is the old one. See here, right? So earlier THD is around 13% or something, right? So now the THD is reduced to 2.9%. See here, you can 2.9%. So you can see this third order harmonic. So earlier it is around 13%. So now it is reduced to only 1%. See here, the third order harmonic is 1.0.3, and now it is 0.8192. It's very small values, right? You see here is some see here this point exact at 0 values, still some disturbances exist. So because of this presence of this 1% third order harmonic. Yeah. So this is about the simulation of a simple bridge rectifier. So not bridge rectifier, boost rectifier. So if you have any doubts, you can ask. So we already discussed in previous classes how to tune this inductor value and this, right? So if you increase the inductor value, the current ripple will be, or the current switching ripples will be. If you are increasing that, the ripples will be reduced. If you are increasing it a higher value, what will happen? The waveform is trying to bend on other side. So that is a point where you need to understand that the inductor value is high. Okay. Similarly, capacitor value, so there is no much tuning is required. So normally 1000 microhenry or so microfarad, or so 4700 microfarad or 2000 microfarad usually sufficient. The only tuning of inductor, so if you keep the less value, for example, I kept around, so in this case I kept around 0.5, right? If you reduce it to some low value, so now I reduced the inductor to 10 times I reduced. Right. So you can observe some switching ripples, or if you are increasing that value beyond that point, right? So what will happen? The waveform will be reduced. because when you increase the inductor, the di by dt will be increased. So that means there is the proper switching will not happen, and the waveform will not track the reference value. See here, now I increase the inductance or decrease the inductance by 10 times. So you can see that some disturbance. Okay. Similarly, if I increase, we already discussed it, if I increase the inductance value for a higher value, so maybe if you increase it to 10 e power minus 3. So now I just increase the inductance higher value. See here, some disturbance is coming, right? The waveform is smooth, right? The waveform is smooth, but some sort of disturbance is there, right? Especially at zero crossings. Clear? So we need to properly select the inductor size, or else we have some mathematical modeling we need to do. So from that we need to actually obtain the inductor value. So all these things we'll discuss. So if you have any doubts, you can ask me. So you have any doubts?
No, sir.
No doubts? So if you have no doubts means I assume that. Okay, I will close the meeting.